Okay, so welcome back to this next video in which we are discussing the Sylow Theorems. Okay, right, so we have now successfully proven the second Sylow Theorem, and we're about to move on to the third Sylow Theorem. But just before we do, what I want to do is tell you about an important corollary of the second Sylow Theorem. And this important corollary is that if you have two Sylow P subgroups of a group capital G, then they actually are always going to be conjugates of one another. Okay, what we have proven so far is that if we have a Sylow P subgroup, a way of getting another Sylow P subgroup is by conjugating that Sylow P subgroup by some element of the group. I want to now show you that if you have any two Sylow P subgroups, you can go from one to the other by conjugating it by some element. Okay, so what I want to show you is that if H1 and H2 are both elements of the set of all Sylow P subgroups of some group capital G, okay, what I want to show you is that there exists some element of the group capital G, okay, and I'll call this element little a. So there exists a little a, which is an element of the group capital G, such that if I conjugate this first Sylow subgroup by the element little a, so if I take a H1 A inverse, this new thing that I get is equal to H2. Okay, so I want to prove that I can go between two Sylow P subgroups by conjugation. I can always go from one to the other by conjugation by an element of the group little a. So I can always find this little a. Okay, and I claim that I can now prove this using the second Sylow theorem. Okay, and this will give you a little taster into why the second Sylow theorem is so useful. So this is a corollary of the second Sylow theorem, and we're actually going to need this corollary to use the proof for the third Sylow theorem. So we're going to use this in our proof of the third Sylow theorem. Okay, right, so how are we going to prove this using the second Sylow theorem then? Okay, well, quite simply what we're going to do is we're going to let H2 equal Rk here. Okay, so to draw a picture, here is our group capital G here, okay, and I'll colour our group capital G in an orange as usual, okay, and then we've got these two subgroups, H1 and H2, and they are both Sylow P subgroups. Okay, and I'll remind you that the order of the group, we're letting this be p to the power of alpha times n. So these Sylow P subgroups, H1 and H2, they will both have order p to the power of alpha. Okay, so that's what it means to be in the set of Sylow P subgroups of G. Okay, so here's H1, and here is capital H2, our second Sylow P subgroup. Okay, and I'll have it in turquoise here. Okay, so what I now want to prove is that I can conjugate H1 by some element of the group and turn it into H2. So the way I'm going to do this is I'm going to use the second Sylow theorem. So I'm going to let my subgroup K be equal to H2. So the K subgroup that appears in the statement of the second Sylow theorem, that's going to be H2. Okay, and H1 is effectively going to take the place of H in the second Sylow theorem statement. Okay, so what I know by the second Sylow theorem is that there will always exist some element of the group, an element little a of the group, such that if I conjugate my Sylow subgroup, which in this case is H1, by this element, so if I conjugate H1 by this element little a and intersect this with my subgroup K, which is H2, okay, this thing is going to be a Sylow P subgroup of my subgroup K, which is H2 in this case, my second Sylow P subgroup. Okay, so that's what the second Sylow theorem tells us, and I should have said at some point that this relies upon this subgroup K having within the prime factorization of its order at least some power of p. Now that is certainly going to be true because the order of H2 is of course equal to p to the power of alpha. Okay, so it's certainly going to be a multiple of p, which is the condition that k needed to satisfy. Okay, so we can absolutely use this second Sylow subgroup, Sylow P subgroup here, as our subgroup k. Okay, so then what happens is the second Sylow theorem tells us that I can conjugate my first Sylow P subgroup here, H1, by some element of the group, intersect that with H2, and get a Sylow P subgroup of H2. Okay, now why is this very, very interesting? Okay, well, what does it mean to be a Sylow P subgroup of H2? Well, it means that you must be a subgroup of order the highest power of P that appears in the prime factorization of the order of H2. But here is the prime factorization of the order of H2. It is just P to the power of alpha. So that means that the order of this thing, the order of AH1A inverse intersect H2, must be equal to P to the power of alpha if it is going to be a Sylow P subgroup of H2. Okay, and what does that mean? That means that it must be equal to the entire group itself. So if you have a group which has an order that is just a prime to a power, okay, so you only have one prime appearing in the prime factorization, then the only Sylow P subgroup of that is the entire group itself, okay, because a Sylow P subgroup must have order the power of P to the highest power that it appears in the order of the group. Okay, so that means that this thing must be equal to the entire group H2. Okay, so I'll just get another piece of paper and I'll write this down then. Okay, so now what I can say then is that this subgroup that I'm getting, which is AH1A inverse, so the first Sylow P subgroup, conjugated by this element little a, intersect H2, is actually equal to all of H2, and that's just because that's the only Sylow P subgroup of H2, because H2 has order P to the power of alpha. Okay, now what does this tell me about AH1A inverse? Well, I am saying I'm intersecting this thing with H2 and I'm getting H2 back again. That means that all of the elements of H2 must be contained within AH1A inverse. So H2 must be contained within the conjugate of this first Sylow P subgroup under the element A. Okay, and the reason for that is that otherwise how could it possibly be true that when I intersect this A conjugate of this first Sylow P subgroup with H2, I get the entire of H2 back again. Okay, that means that every single one of the elements in H2 must have also been in here. Okay, so I can validly write down that H2 must be contained within AH1A inverse. Okay, right. On the other hand, what do I know about the order of AH1A inverse? Well, it's going to be the same as the order of this first Sylow P subgroup, which is P to the power of alpha. Okay, i.e., this thing has the same order as H2. Okay, so that tells me that, in fact, this thing must equal H2. Okay, so what I can now write down is that H2 must, in fact, equal AH1A inverse. So what this has thus told me is that if I take any two Sylow P subgroups of my group capital G, there will always exist some little a that I can use to conjugate the first of my Sylow P subgroups to turn it into the second of my Sylow P subgroups. Or in other words, all Sylow P subgroups of a group capital G are conjugate to one another. Okay, right, and we're going to make great use of this fact in our proof of the third Sylow theorem. Okay, so now let's actually state what the third Sylow theorem says. Okay, so the third Sylow theorem, again, it's a reasonably nice and easy one to understand. Okay, so we saw how the first Sylow theorem, that was nice and easy to understand what it actually said. The second Sylow theorem was not so easy to actually understand what it was saying, but the third Sylow theorem is a nice, obvious one, what it actually means. Okay, so the third Sylow theorem is absolutely all about asking the question, how many Sylow P subgroups are there in a group capital G? I.e., what is the order of this set of all Sylow P subgroups in the group capital G? Okay, and the first thing we'll do is we'll just give a shorter symbol to mean this thing here. Okay, so the symbol that is often used is n subscript p. So when I write n subscript p from now on, that's just going to mean the actual number of Sylow p subgroups in that group capital G. And what I've shown you so far now is that in fact all of the Sylow p subgroups are just going to be conjugate of one Sylow p subgroup. Okay, so that's going to be useful for gaining some insight into what this number actually is. Okay, so the third Sylow theorem does not tell you the actual value of this. It doesn't give you an explicit formula for what this is equal to. Instead, it tells you some useful things about it. So it gives you some useful properties of it, but as I say, you're going to be disappointed if you're expecting an explicit formula for what the number of Sylow p subgroups is actually going to equal. Okay, so the third Sylow theorem comes in two parts. There are two pieces of information that the third Sylow theorem gives us about this number. Okay, and the first one is that this number, whatever it is, will always divide little m. Okay, and let me remind you of what little m actually was equal to. So remember, little m was that portion of the order of the original group capital G that was left over after we pulled out highest power of p. So the order of the group capital G was equal to p to the power of alpha times m. So m was what was left of the prime factorization after we pulled out that highest power of p that we could. Okay, so what this first portion, and I might just put a little 1 here, a little I, so this is the first part of the third Sylow theorem. What this first part of this third Sylow theorem is telling us is that this number, it is part of the prime factorization of m here. Okay, so if we took its prime factorization, the powers of the primes that we'd find in here would be completely within this little m portion. Okay, so notably, it is not a multiple of p, so it has no powers of p appearing in its prime factorization, just like m has no powers of p appearing in its prime factorization. So that's the first part of the third Sylow theorem, and the second part of the third Sylow theorem tells us that this number is actually going to be congruent to 1 modulo p. So this is modular arithmetic here. Okay, so this number, whatever it is, will be congruent to 1 modulo p. Now let me give you a more normal equation for what that means. That means that this number, np, the number of Sylow p subgroups in the group capital G, is going to be equal to some multiple of p, some natural number multiple of p. So little n here is some natural number, a counting number, 1, 2, 3, 4, 5, a positive integer basically, okay, times p plus 1. So saying that it is congruent to 1 modulo p is equivalent to saying this. It's equivalent to saying that it's 1 greater than a multiple of p basically. Okay, the number of Sylow p subgroups in the group capital G is always going to be congruent to 1 modulo p. It's always going to be some multiple of the prime p. Okay, and in the case of counting Sylow p subgroups, this will always be a natural number because we'll always want the overall answer to be a positive number. More strictly speaking, when you say that something's congruent to 1 modulo p, this could actually be any integer multiple of p. Okay, but logically here we are talking about a positive integer here. Okay, so this must be a positive integer multiple of p that we're going to have here. Okay, but more strictly talking about what this actually says, i.e. what it means in terms of modular arithmetic, this would be z rather than n. But because we're talking about a positive number, we can just replace that with n. So it's going to be some multiple of p, some positive multiple of p in this case, plus 1. So it's 1 greater than some positive multiple of p is what that says. Okay, right. So we're going to prove both parts of this third Sylow theorem, and we'll start obviously with part 1, which is slightly easier than part 2. Okay, but it's quite nice because part 2 builds on the proof of part 1. So we'll start by proving part 1, and then we'll just basically continue the proof on to get to part 2. Okay, right. So the way that we're going to do this then is once again using group actions. Okay, so everything that we're doing here uses group actions. Okay, and we're going to have a group action of the group G on this set of Sylow P subgroups. So let me show you this once again. Okay, so we'll draw a group action composition table here. Okay, we'll call it dot once again, and we'll put all of the elements of the group down here. So we'll give every element of the group a row in this group action composition table, and I'll colour all these entries in red here. And then we'll put all of the elements of the set of Sylow P subgroups in G up here. So all of the elements that we'll actually be acting on here are going to be Sylow P subgroups of the group capital G up here. Okay, so we'll colour those up there in turquoise here. So all the Sylow P subgroups are given a column that's being dedicated to them. Okay, right. So now what I need to do is actually define what the entries in this group action composition table are actually going to be. So some element of the group little g acting on a Sylow P subgroup, which I'll denote capital H. Okay, so drawing this on as always, we'll have the row dedicated to the element little g here, and then we'll have the column dedicated to the subgroup capital H up there, and this G dot capital H refers to this entry in the group action composition table. The way we're going to define this is we're quite simply going to define it as the conjugate of the Sylow P subgroup capital H by the element little g. So this is going to be GH G inverse. Okay, so conjugate all the elements of the Sylow P subgroup by little g, get a new Sylow P subgroup. Okay, and that's going to be your answer. So this is looking hopeful that it will be a group action, because of course all the answers that we get here are going to be Sylow P subgroups back again, because whenever you conjugate a Sylow P subgroup by some element of the group, you get another Sylow P subgroup. So from that point of view, it's looking hopeful. What we now need to make sure of is that it actually obeys the axioms of a group action. Okay, so let's just check those. So again, axiom number 1, and you're probably getting sick of these axioms now, but we need to check them. Okay, so axiom number 1 of a group action says that for whatever two elements of the group you pick, so for all G1 and G2 that you pick from the group capital G, and for all elements that you pick from the set, so all Sylow P subgroups that you can possibly pick from the set of all Sylow P subgroups in G, okay, it must be the case that, and I'll write it in a moment, it must be the case that G1 dot G2 dot H is equal to G1 composed with G2 dot H. So again, as always, this just is the statement that this group action composition table needs to play nicely with the group composition table. It needs to be consistent with the group composition table. Okay, so how are we going to prove this? Well, as always, we're just going to apply the definition, and really it's going to be very, very obvious. Okay, so let's take the left-hand side here firstly. So if we firstly act little g2 on our Sylow P subgroup capital H, then what we'll end up doing is conjugating all the elements of our Sylow P subgroup capital H by G2, so we'll get G2 capital H G2 inverse. Okay, so that'll be the answer to this middle bit. Okay, we'll conjugate all elements of that Sylow P subgroup by G2. Then when we act G1 on this, we'll end up conjugating all the elements in here by G1. So we'll do G1 of this thing, and then G1 inverse. Okay, so as a set, what will this equal? It'll equal all things of the form G1 conjugating something of the form G2 H G2 inverse, and then we'll have G1 inverse over here, where little h is an element of my Sylow P subgroup, capital H. Okay, so you firstly conjugated all of the elements of the subgroup by G2, and then you've conjugated them all by G1, and you've got all of the remaining answers in a set, and that is going to be your new Sylow P subgroup. That's the answer to the left-hand side here. Okay, now let's consider the right-hand side. So here we'll just have the entry the element of the group G1 composed with G2, and we'll be acting that on H. So what we'll want to do is conjugate this subgroup capital H by the element G1 composed with G2. Okay, and we'll end up with G1 composed with G2, H G1 composed with G2's inverse. Okay, so as a set, this will equal all things of the form G1 composed with G2, little h, and then we'll have G1 composed with G2's inverse, and little h will be an element of the subgroup capital H. Okay, so we'll just go through and conjugate all of the elements of our Sylow P subgroup by this element G1 composed with G2. Okay, but of course these two sets are identical to each other because all we need to do is replace the G1 composed with G2's inverse with G2 inverse composed with G1 inverse. Okay, so we just need to rewrite this like so, and then of course we know that all of these compositions are done in the group, so it really doesn't matter where the brackets are, that's associativity. Okay, so this thing is equal to this thing, whatever little h you're working with. Okay, so for all little h in the subgroup capital H, this thing will equal this thing, and therefore these two subgroups that you end up with will be identical to one another, so the two sides of this equation will match up. Okay, so axiom number 1 of a group action then is going to be satisfied. Okay, so then it's just the easier one, which is axiom number 2 of a group action. Okay, and this just says that the identity element of the group must act on any Sylow P subgroup to send it onto itself. Okay, and that must be true for all Sylow P subgroups in our set of all Sylow P subgroups of G, which is the set on which the group is acting. Okay, so why is that going to be true then? Okay, well the reason for that is that the identity acting on a Sylow P subgroup capital H just means take all the elements of that Sylow P subgroup capital H and conjugate them by the identity. When you conjugate a bunch of elements by the identity, that has absolutely no effect whatsoever, so you'll end up with the exact same Sylow P subgroup back again. You'll end up with capital H. So indeed the identity will act on any Sylow P subgroup, any element of our set, and send it onto itself. So that's the second axiom of group action satisfied. Okay, right, so what we're now going to consider is the orbit of this group action, and again it's orbit in the singular. There is only one orbit. This group action is going to be a transitive group action by the group on this set of Sylow P subgroups. So if I draw my set of Sylow P subgroups here, so this is my set of all Sylow P subgroups of the group capital G, and what colour should I denote it in? I think I'll colour it in red here. Okay, let's now consider the orbits that this group action will partition this set up into. Okay, well I claim that this is actually going to be a transitive group action. Okay, there's only going to be one orbit and it's going to be the entire set. And the reason for that is if I consider one element of this set, so the Sylow P subgroup capital H, and let's consider what the orbit of that Sylow P subgroup capital H is actually going to be equal to. Well, that's going to be all Sylow P subgroups that it can be mapped onto by elements of the group acting on it. Okay, but we know that if you have any other Sylow P subgroup in here, I can always find an element of the group that I can conjugate this one by to get that other element. Okay, that's the corollary of the second Sylow theorem that I just showed you. Okay, any two Sylow P subgroups are conjugate, so I can always turn this one into any other Sylow P subgroup by picking the element of the group that I'm going to use to conjugate it properly, basically. Okay, so if I go through and conjugate this by every single element of the group, which is what I'll do if I wanted to construct the orbit of capital H. So if I wanted to construct the orbit of capital H, what I do is go through all the elements of the group and act them on this Sylow P subgroup capital H. So I let G vary over all elements of the group, and remember that the action just means conjugate that subgroup by the element little g. Okay, so I'll just take all of the conjugates of this Sylow P subgroup by elements of the group. Okay, and of course what I will then be able to get is any element of this set of Sylow P subgroups. So this will actually equal the entire set because I know that I can get to any Sylow P subgroup by conjugating this one by some element of the group. Okay, so that's why this must be a transitive group action, why there can only be one orbit in this group action. Okay, right. So what we can now do is apply the orbit stabilizer theorem, because the orbit stabilizer theorem still applies even though there is only one orbit. So we can say that the order of this one orbit, which of course is the order of the set of all Sylow P subgroups of our group capital G, which is this number NP, the number of Sylow P subgroups in the group capital G, okay, this is going to be equal to the number of left cosets of the stabilizer of an element within the set of all Sylow P subgroups of the group G in the group capital G. Okay, so this is going to be equal to the order of the group divided by the order of a stabilizer of, let's just say, this Sylow P subgroup capital H here in the group capital G. Okay, so again, I've just applied the fact that we're working in a finite group here to say that the index can be replaced with this quotient here. Okay, right. So let's now think about what this thing here is here. Okay, the stabilizer of this Sylow P subgroup capital H in the group capital G. Okay, so, whoops, don't want the order of it yet. So let's just think about what this thing actually is going to be equal to. Okay, so this is going to be all the elements of the group, all little g is an element of capital G, such that when I act little g on capital H, I get capital H back again. But that means that when I conjugate capital H by little g, that just means act little g on capital H, okay, I must get capital H back again. Okay, so all of the elements of the group, which if you use them to conjugate this Sylow P subgroup, have absolutely no effect on it. They send it onto itself. Okay, now I can rewrite that condition in a way that's slightly more helpful. Okay, and in fact, I think I'll go over the page to rewrite it. Okay, so now what I'm going to do is rewrite the condition for an element of the group to be in the stabilizer of this Sylow P subgroup capital H in the group capital G. Okay, so this is going to be all elements of the group, all little g is an element of the group capital G, such that if I use little g to conjugate any element of my subgroup capital H, I must get another element that is in the subgroup capital H. Okay, I cannot go outside of the subgroup capital H, otherwise when I conjugate the entire subgroup, I wouldn't actually get the subgroup back again. So this must be true for all little h as an element of capital H. Okay, so remember that's just because when you conjugate a subgroup by an element of the group, all that means is conjugate all of the elements in that subgroup by the element of the group. Okay, so all I'm saying now is that if I conjugate all the elements of the subgroup capital H by little g, I must get some other answer that's in the subgroup capital H. Okay, and that's equivalent to saying that when I conjugate the subgroup capital H by the element little g, that I get the subgroup capital H back again. Okay, because remember this will be a bijective map. Okay, so not only, well, if it's the case that all of these answers are in capital H, then when you vary this over all elements of capital H, you will get the entire subgroup capital H back again because of the fact that conjugation is a bijective map. Okay, so what I'm saying is, if this is true, it won't be the case that when you conjugate all elements of the subgroup capital H by G, you end up somehow with a subset of capital H back again, okay, because of the fact that this is bijective, so it must then map all of the elements of capital H onto all of the elements of capital H, so you'll end up with the entire subgroup back again. Okay, right, but we have seen this definition before. This is the definition of the normalizer of the Sylow P subgroup capital H in the group capital G. This is how you define a normalizer of a subgroup capital H in a group capital G. It's all elements of the group which, if you use them to conjugate elements of the subgroup capital H, you get another element back within that subgroup, basically. Okay, so it's all elements that, if you use them to conjugate an element in the subgroup capital H, give you something else that's back in the subgroup capital H. Okay, so what we can now say then is that the order of the set of all Sylow P subgroups, NP, is equal to the order of the group divided by the order of the normalizer of H in G. Okay, and we're very close to having proved that first portion of the third Sylow theorem now. Okay, all we need to do now is fill in what the order of the group is actually equal to, and we'll be very close. Okay, so this is going to go to the number of Sylow P subgroups in the group capital G is equal to p to the power of alpha times m over the order of the normalizer of H in G. Okay, now all we need to do is explore what the order of the normalizer of H and G is actually going to be in a bit more detail, and then we'll be there. Okay, so how am I going to do this? Well, let me just draw a picture to explain this. So, nice simple picture as always. So we've got the group capital G here. Okay, and I'll colour the group in green here, like so. Okay, and we'll then have our Sylow P subgroup of the group here, which is capital H. Okay, now we have now constructed this thing called the normalizer of the subgroup capital H in the group capital G. And my big claim now is that capital H is going to be a subgroup of the normalizer of H and G. Now we proved this in the video on centralizers and normalizers, and in fact it turns out that capital H will be a normal subgroup of the normalizer of H and G, but all we need at the moment is that H will be a subgroup of the normalizer of H and G. But let me just argue for why capital H will be a subgroup of the normalizer of H and G. Okay, so the reason is that capital H is going to be completely contained within the normalizer of H and G, because any element that's in the subgroup capital H itself, if we use that element to conjugate all the elements of capital H, we will indeed end up absolutely always with other elements in capital H. So if little g here is some element of the subgroup capital H, when you conjugate any element of the subgroup capital H by some other element of the group subgroup capital H, you will indeed always end up with some final element in capital H, because capital H is closed under composition. Okay, so indeed all of the elements that are in capital H will be within the normalizer of capital H in G. So what I can do is draw on here the normalizer of capital H in G. Okay, and it will completely contain the subgroup capital H here. So I'll colour it in red there. So capital H is completely contained within the normalizer of H in G. Okay, and that means that capital H is a subgroup of the normalizer of H in G. Okay, which itself is a subgroup of capital G. Okay, now it will be a normal subgroup, but that doesn't matter for our purposes at the moment. I'll just briefly say why it will be a normal subgroup, because we will use that later on in the proof of the second portion of the Sylow's third theorem. Okay, it will be a normal subgroup because if you take any element from this larger group, the normalizer of H and G, and use it to conjugate any element of our subgroup capital H here, you will always get another element in capital H because of the very definition of the normalizer of H and G. Okay, which means that H will be normal in its normalizer, and that's why it's called the normalizer of H and G. Okay, but as I say, we don't actually need that at the moment. All we need is that capital H will be a subgroup of the normalizer of H and G. Okay, why do we need that? Because we can now apply Lagrange's theorem. Lagrange's theorem tells us that the order of the subgroup capital H must divide the order of the larger group, which in this case is the normalizer of H and G. Okay, so this is going to be really, really powerful, because what do we know about the order of this subgroup capital H? Well, it is p to the power of alpha, okay, because it's a Sylow P subgroup. So that means that the order of the normalizer of H and G must be a multiple of p to the power of alpha, i.e. this portion here must contain the p to the power of alpha, okay, completely. Okay, otherwise it will contradict capital H being a subgroup of this, okay, because capital H's order wouldn't divide the order of the normalizer of H and G. So the order of the normalizer of H and G will be p to the power of alpha times some m bar. Okay, so that means that the p to the power of alpha here will cancel with the p to the alpha here. So I'll get rid of them now. And what we'll end up with is this equation that the number of Sylow P subgroups is equal to m divided by m bar, where m bar is just some part of m. Okay, so if we have the prime factorization of m, the prime factorization of m bar will just contain some portions of that, some powers of the primes that appear in the prime factorization of m. Okay, so what you'll end up with for the number np here, the number of Sylow p subgroups in the group capital G, is that it's just some part of the prime factorization of m, okay, i.e. it divides m, okay, it is some part of m basically, okay, its prime factorization just contains some powers of primes that are completely contained within m. M is a multiple of the number of Sylow p subgroups in the group capital G. So that then is the proof of the part 1 of the third Sylow theorem. Okay, we'll take a break there, and in the next video what we'll do is prove part 2, and it's nice because it will just basically be a continuation of this proof. It will use the same group action.